Hi, I'm Shreyas, and I'm going to be talking about the effects of spatially distributed kinetic constraints on systems which are known to be classically chaotic. And this project has been done in collaboration with Prof. Manas Kulkarni and Stithidi Roy. Let me just motivate why chaos is interesting in the first place. Chaos as a concept shows up in lots of areas of physics, and not just physics, everywhere. It shows up in population studies in microbiology, all the way up to describing black holes, the dynamics of black holes. So chaos is very interesting to study. Traditionally, classical chaos has been studied using Lyapunov exponents. And it's understood as a phenomenon where trajectories that are infinitesimally close by start diverging pretty quickly, known as the butterfly effect. The question now turns up, how do we study systems that are quantum chaotic, because there's no direct generalization of the Lyapunov exponent. To study that, there's the OTOC, which is known as the out-of-time ordered correlator, which has emerged as a diagnostic tool to study information scrambling in quantum chaotic systems. OTOCs are specifically good to look at spatio-temporal spread, as opposed to just temporal spread that you could learn from with a Lyapunov exponent. Now, to come back to a classical system, we would like to study spatio-temporal spread in classical systems as well, as opposed to just temporal spread. For this, we look at a classical analog of the out-of-time ordered correlator. And specifically in the rest of the work, since I'm going to be dealing with a spin chain, we look at the classical analog for a spin chain. It's simply, so the analog comes out to be simply nothing more than the cross correlator between two copies of a spin chain that have been initialized in slightly different conditions. So now that we've established the probe for classical chaos, I would like to talk about why we care about introducing constraints in the first place. Ergodicity in general, it just means that when you average, like after a system is ergodic where if after a certain amount of time, averaging over space and averaging over time essentially yields the same results for observables. And this is what conventional statistical mechanics describes for us. However, there are certain systems where ergodicity simply doesn't hold. And one way of impeding ergodicity is by preventing dynamics happening in time. And for this, kinetic constraints plays a crucial role. And so we ask the question, what happens to classical many-body chaos when we introduce constraints into the problem? Kinetic constraints specifically. So let me just describe the system that we're dealing with. The system is simply a time periodic Hamiltonian, which operates only on the Z component of spins for a certain amount of time, and then the X component of spins for a certain amount of time. And this is just for convenience because the dynamics of such an equation can simply be written as a product of two rotation matrices, one along the Z-axis, one along the X-axis. And the constraint that we include is that the dynamics only happens if the constraint function return is 1, and otherwise there is no dynamics if the constraint prohibits the dynamics from happening. So the constraint that we put in is nothing, is simple. It's a spin at site I is constrained if both of its nearest neighbors lie in a prohibited zone of their own block sphere. So the schematic should, for example, the spin at x minus 1, it's frozen because x minus 2 and x plus 1 both lie within the grayed out region of their own block spheres. So at this time step, the spin at x minus 1 will not evolve, but the spin at x will evolve because the spin at x minus 1 is outside the zone, outside the prohibited zone, and so the spin at site x can evolve in time. So now that we've established this, we would like to know what happens to the decorrelator as mentioned before. The decorrelator, as I said, was just this cross correlator between two spins. So and this theta I here is the parameter that describes the blocked off zone. So theta is a function that is the angle from the vertical that describes the prohibited zone. So if theta were equal to 0, that means that the kinetics is completely unconstrained, which means and And so for theta equal to 0, we have completely unconstrained dynamics and the decorrelator as a color map in space versus time shows classic linear light cones that are a hallmark of chaotic systems. The linearity shows that that the spread of perturbations in such a system happen with a finite speed, which is called a butterfly speed, which can just be thought of as the speed of sound through such a system. And similarly, for theta equal to pi, for example, there would be absolutely no dynamics and perturbations wouldn't spread at all. As we increase theta from 0 to pi, however, we can see that for one, because the constraints increase, the spread of perturbations slow down, and hence the velocity of spread becomes slower, which is why the light cone becomes steeper. And further, there's also a broadening of the front of the light cone, which shows that due to competing effects between wanting to spread and being prohibited from spreading, the OTOC front is stretched out, and it turns out that this stretch is diffusive. The interesting thing here is that between that at a value of theta, which is around 0.53, there is a rapid slowing down of this light cone. And at 0.6, the light cone is entirely frozen. This shows that there must be some sort of dynamical phase transition at around theta equals 0.53. And above that critical constraint angle, the spread is completely frozen. So given this, it's worth asking what happens if we introduce disorder in the constraints, because introducing disorder in the constraint is interesting because if we're around the aforementioned critical point of around 0.53 and introduce a distribution in the critical angles, in the constraint angles, we might have some angles that are below the critical point and some angles that are above the critical point. And we would like to know what happens to the spread of the light cone in such a case. So these values here so the constraint angle is now drawn from a distribution with mean theta bar and width 2 times delta theta. So the interesting thing to note here is that as we introduce a width which takes the angle, theta bar 0.4 and delta theta 0.4 means that the values of the critical angle can range from 0 to 0.85. So the interesting thing here is that in some of these plots, it appears like as if the light cone itself is bending upwards, which is an interesting thing because a light cone bending upwards means that the spread is now sublinear, and sublinear spread of perturbations can indicate systems that are no longer chaotic. So given that we have this form of the decorrelator, we would now like to see if we can establish some sort of scaling collapse for the decorrelator. For the case of no width, we know that with a linear light cone and diffusive spread, the decorrelator can just be fit to a complementary error function form, where xv denotes the butterfly velocity term, which goes as t to the 1, and xi t describes the diffusive term, which goes as root t. Since the form of the OTOC still looks similar, we fit it to the same function, except we allow the power laws to be different. So we assume that there's a power law with alpha and beta instead of 1 and 0.5. Or rather, here alpha would be 1, and since xi squared, beta would also be 1. We just we try to see if we can fit alpha and beta to some other values. So upon introducing the constraints, we can see that once again, the form of the OTOC shows a pretty good complementary error function type form. The first plot shows is a standard 0 width case where the different plots indicate longer and longer times, and we find values of x, v, and xi that allow it to collapse to this. Similarly for all of these cases. And given that the collapses are so good, we look at what the values of the exponents alpha and beta are as defined before. Alpha being the velocity, and so because we're looking at sublinear spread of the OTOC, we are interested in the alpha exponent because this is what describes whether the decorrelator spreads ballistically or subballistically, linearly or sublinearly. Alpha equal to 1 implies linear spread, and alpha less than 1 would imply sublinear. So this plot shows what the decorrelator looks like. we can see that in general, we can divide this region into three regions. The leftmost is a trivially ergodic region where even with the distribution, all the angles of every site is well under the critical zone. So we don't expect anything phenomenologically different over here from the original system. And neither do we in the rightmost region, which is a trivially frozen region, because all the angles are well above the critical angle. The interesting zone is in the middle, where we can see that there indeed is the alpha does take a range of values that are neither 1 nor 0. And that is interesting because, once again, this could imply that there's sublinear light cones that are happening here. And that could imply that the system, due to the distribution of constraints, is no longer chaotic. Finally, we just look at the activity of the system as a whole, because the activity lets us know whether the system is conducive to dynamics happening in the first place. So the activity is simply defined as the global activity is simply defined as the site average constraint function. And the question is, is there a region where the system remains active? That is, the activity of the system is saturated to a finite value, but the light cone shows that the perturbations no longer spread linearly. So just to look at the case for delta theta equal for the width for no width, looking at the case for no width, we can see that for certain values of theta, this is very close to the critical point. The activity saturating here is what I mean by global activity being high. And right after the critical point, which is at around 0.523 pi, we see that the activity decays very quickly. So the question now is once again to see whether there exists regions in the parameter space where the activity is finite like this, but the OTOC spreads sublinearly. And this, just give me another minute. And this is, so to conclude, this is that interesting zone where the middle red line now shows the transition in activity. It's to the left of this line, the activity is finite and saturates. To the right of this line, the activity decays. And in this middle zone, there exist values of the decorrelator which are between 1 and 0. So there's a wide parameter zone where the OTOC is spreading sublinearly, but the activity indicates that the system should be chaotic, just like indicates the system should be chaotic. And because the parameter region is large, this could be indicative of either an anomalous phase. So an interesting thing is that as the width, so this anomalous behavior happens if you look at the region close to the critical point, this anomalous behavior happens in regions that are larger and larger as width increases. So it could either be indicative of an anomalous phase or some sort of crossover region, which seems to keep increasing as the width goes up. And one way to figure out whether which one this is to look at any critical exponents across this transition and to look at the long time behavior of how this region changes as you evolve the system for more and more time. Thanks.